In this video, I'll talk about how to implement differentiation in MATLAB. We'll go over a handful of strategies. After studying this video, you should be able to use the MATLAB functions diff, gradient, and Polydor to compute derivatives of data, and functions for that matter. Should also be able to implement differentiation strategies for unequally spaced data. Recall that the finite difference approaches assume equal data spacing. And you need that assumption in order to define some delta x equals h for all data points. So first let's talk about using MATLAB's diff function. The diff function actually is not a differentiation function, it's just a function that returns the differences between adjacent elements in the input x. So for example, if x is equal to a vector 1, 2, 4, then diff x would be the differences of those adjacent elements. So it would be 2 minus 1 or 1, and 4 minus 2 or 2. So the output will always have one fewer elements than the input. We can use the diff function to develop a finite difference derivative approximation. If we have data in vectors y and x and just take diff y divided by diff x, that's like delta y over delta x for each of those vectors. And then relating this back to the finite difference approximations, that would be a forward difference if you assign the values of dy dx. Recall there's going to be one less value in dy dx, one less element than there is in x and y. If you correlate those values to the 1 through n minus 1 elements of x, so starting with the first element of x, then we're going to be calculating a forward difference. If you correlate the values to the second through last elements of x, then we're calculating a backward difference. So this calculation is either a forward or a backward difference, just depending on where you correlate the results to, whether they're looking forward or backward in calculating those differences. The simplest, more accurate option that we saw in the numerical differentiation video would be a centered difference that's second order, using points that bracket the point at x. You could construct a centered difference approximation using diff, but MATLAB actually has a better function for doing that, and that's the gradient function. And the gradient function takes as an input f, which is data points, and h, which is the spacing. So notice that this requires, we're making an assumption that that is equal spacing. We didn't make that assumption with diff. Diff would actually work for unequal spacing. So this is going to return the derivative of the data in f at each of the points, and the output vector has the same number of points. It uses a forward difference for the first point, since we can't use a central difference because there's no -1 point, a backward difference for the last point, and centered differences for the interior points. And these are the order h squared, second order central differences. So h is the spacing between points. If you leave that out, there's a default that just says h is equal to 1. So generally you would include that. And again, the data must be equally spaced, since this is just implementing that centered finite difference formula, dy dx evaluated at x sub I is equal to f at x I plus 1 minus f at x I minus 1 over 2h. So for h to be defined, we have to have equally spaced data. So it's a second order calculation. It returns derivatives for every point in f. So it's better than the diff approach in general if the data is equally spaced. One note is we are using first order for the first and last points. So the gradient function can also be used to find partial derivatives for matrices. We won't spend too much time doing this, but if you provide, if F is a matrix, then df dx, df dy dx will be the partial derivatives with respect to x and the partial derivatives with respect to y in that matrix F. And I would encourage you to experiment with that in MATLAB if you're interested in pursuing that further, but we are not going to focus on doing partial derivatives in this class. Another function MATLAB has that's kind of convenient is the Polydor function, and the Polydor function is for differentiating polynomials. And this is actually an analytical calculation because it's so easy to calculate the derivative of a polynomial. Recall how MATLAB stores polynomials as a vector of coefficients. So if we input a coefficient vector p, this function Polydor is going to output the coefficients of the derivative of p. So it's the exact same result that we could do ourselves with two MATLAB commands. So again, this is an analytical result, and if we have that polynomial defined as p1 x to the n minus 1, p2 x to the n minus 2, again for an nth degree polynomial, sorry, an n minus 1th degree polynomial with n coefficients, then if we just drop, again when we take that derivative, we would drop the last coefficient and then multiply the rest of the coefficients by decreasing constants as we go through. So the way that this would work, let's say this is a third, let's say we started with something like 4x cubed plus 2x squared plus 3x plus 1, if that's our polynomial, then this first command would leave us with 4, 2, and 3. And then the next command, we would take the first element and multiply that by length p, so that would be 4 times 3. The second element, incrementing -1, so that would be 2 times 2. And the third element would be 1, so that would be 3 times 1. And we end up with 12, 4, 3, which is the exact same thing that we get by taking f prime, is 12x squared plus 4x plus 3. So, as I said, this is an exact result for the derivative of a polynomial. So if we want to do higher order differentiation schemes, for example, talked a bit about fourth order centered differencing, we need to write that code ourselves. So here's an example function M file for calculating a fourth order centered difference approximation. So it's going to assume equally spaced data and just take h from the first two data points. And then we'll use a second order forward difference approximation for the first 2 points. So there's a second order forward difference approximation for the first 2 points because we need to get to the third data point before we can use that fourth order centered difference formula because it includes k minus 2 and k minus 1 points. And then we have to stop at 2 short of the last data point because we need the k plus 1 and k plus 2 data points. So we'll stop there and use second order backward differences for the last 2 values. So you can download this M file and play with it and use that for fourth order centered difference approximations. So let's talk about a couple implementation notes. So the approaches that we've talked about generally require equally spaced data so we can define H. We call it equal spacing. That's necessary to define H that's consistent for all the data. There's a couple approaches for calculating derivatives of unequally spaced data. One way is to determine a polynomial fit and take its derivative at the point that we want. So for example, we can do this analytically using a second order Lagrange polynomial to fit 3 points and then take its derivative. So you would have here, we can use any 3 points and this would be a derivative that we've developed using a second order Lagrange polynomial fit through those 3 points and then taking that derivative. So this result here is what you get after taking that derivative. Another approach is to use a spline, and we can use a spline to generate equally spaced interpolated data from our unequally spaced data that we're trying to differentiate, and then we can use any finite differencing scheme on that equally spaced interpolated data. So for example, we could use a fourth order center difference. As I said earlier, the Diff function approach doesn't require equal spacing, but that's only a first order approximation. So it's generally better to take one of these other approaches. Now, one other consideration is if the data has errors. So if this is experimental data with some uncertainty in it, one thing that happens is finite difference derivative approximations will tend to amplify the errors in the data. So we can see that if we're imagine a line going through every data point. So here's smooth data with no errors. And taking the derivative dy dt indicates a steadily increasing slope or derivative of that data. But now we introduce even relatively small errors. But those small errors are going to lead to large changes in slope between the points. And so we see here that those errors are amplified in terms of MATLAB calculating, or in terms of calculating those slopes. And in fact, here we show the slope decreasing when it should be increasing, again, due to that amplified error when taking that derivative. So an approach to address this is to use a curve fit. We can take a curve fit of the data to smooth out the errors. Now once we have a curve fit, that's going to give us a mathematical model. So we're not necessarily working with the data directly once we have some mathematical model f of x, and we can just differentiate that mathematical model analytically using the techniques you learned in your calculus class. So in summary, when you're differentiating data, if the data has errors, it's generally going to be best to take and apply a curve fit to the data to smooth out or average out those errors using that least squares fit, and then just take an analytical derivative of your mathematical model. If you're differentiating really accurate data and it's unequally spaced, then it makes sense to use interpolated data to calculate that derivative. And that concludes this video.